Okay, so this problem is problem number 2 on the homework, or 3.25 in Schroeder, and it's looking at that Einstein solid that we were looking at in the previous problem set. So part A is pretty straightforward. Essentially, we're given omega from that problem that we did in the previous set. So that's basically we just have to plug it into our equation for entropy. And then I brought down the exponents and separated the terms using a couple rules of logarithms. So yeah, that's our answer here. The next part asks us to calculate the temperature as a function of energy. And we know that the derivative of entropy with respect to energy is 1 over T. So we just need to take the derivative of the answer to part A with respect to energy. And we're given the relationship Q equals energy over epsilon. So here I just plugged that in and then took the derivative. And then when you simplify all of the terms, you'll see that all of these cancel out. So after taking the reciprocal of this result here, we're left with this function for temperature right here. Next, we need to do a bit of algebra to solve that result for energy. And then we can take the derivative of that to find the heat capacity, since du dt is the heat capacity. So after applying a couple of chain rules, this is the answer for that part. Next, we need to use an approximation for when T is large. So we can use that equation for U as a function of temperature from earlier and approximate e to the epsilon over tk. We approximate that as 1 plus epsilon over tk. So we have U equals ntk, and then we just have to take that derivative with respect to temperature to get heat capacity, so we get the desired result of nk. Below is a graph that I plotted in Desmos for part E. I substituted in little t for epsilon over kt, and then also moved nk to the other side to avoid dealing with those all those units, so we only have unitless values. So as you can see, as T approaches 0, the heat capacity also approaches 0, which makes sense given the third law of thermodynamics, which gives this relationship here. We know that as T goes to 0, the entropy reaches 0 as well because we have a multiplicity of one state. But what that means is our lower bound of the integral would blow up to infinity unless the heat capacity also reaches 0 at this point. So this answer makes sense. Moving on to the materials, I used figure 1.14 in Schroeder to find values for temperature. The process is a little bit weird, but basically I found values for little t on my graph in Desmos where the heat capacity was 80%, 60%, and 40%, that percentage of its maximum asymptote value. And then I used the figure here to determine temperatures for those values of T. So I guess I should give an example. So for lead, for example, I found that when it was 80% of its maximum, the temperature was 40 Kelvin, and then that's using a little t value of 0.6 because that's where it was 80% on the Desmos graph. So essentially I'm just like adding units to my unitless graph and then approximating a lot by drawing these lines. But yeah, I think that's what we were supposed to do for this. So here are the values that I got for each of the materials. Oh, and also I used the conversion factor of like the charge of an electron to get from joules to electron volts. So that's how that happened. So this last part was just sort of a lot of algebra. I took my result from part C, but instead of approximating like we did in part D, I actually approximated the equation for heat capacity and then kept all of the terms through x cubed. So these were my steps. I factored out epsilon over kt squared, which canceled out a lot of stuff in the front and then made my denominator easier to work with. I then expanded the denominator through a foiling process with 3 terms, and I got rid of anything with a higher exponent than 3, including one term in the numerator, so don't forget about that one. And then this part took me a bit of time to figure out, but I eventually found that I should use a binomial approximation with 3 terms to bring the denominator up to the numerator using a value of -1 for n. And then once it was all written out, I realized that the only important term from the third term of the approximation was the epsilon over kt squared one, since all of the others were going to be too small. So after I did that, I did a similar process of foiling out and then getting rid of all of the small terms, and a couple of terms canceled, which left me with the result that we were looking for here. So yeah, that's the end of the problem. It was a long one, but other than a few algebra tricks, I don't think it was too bad. Of course, let me know if you have any questions, and I'd be happy to answer them. And yeah, that's basically it. Hopefully, the end of the sickness is near, and I'll be back in class soon. Yeah, thanks for watching.